Okay. My name is Adolfo, and I'm going to talk about the role of water, CO2, and non-innocent ligands in the CO2 hydrogenization to formate that compound using DFT and AMD. A- A-
AIMD, yeah.
yeah, that's okay. Alright. So CO2. CO2 is one of the most abundant gases in our atmosphere because we burn a lot of hydrocarbons. So we kind of know what to do with it. And because we have so much of it, we're trying to catalyze it to use it in different industries and get something out of it. So right now as this paper, they're using it to catalyze carbohydrate like CO, methane, methanol, formic acid, dimethyl ether, dimethyl formate, carbonates, and carboxylic acids. In this paper specifically, we're more interested in the formic acid because it can be used as a form of energy or like a fuel. So the analysis method they did was the DFT, which is density function theory. That's the same we're using our Gaussian calculations, and AIMD, which that busy set actually recreates the conditions of the reactions in the lab without you actually running the experiment. First, to be able to understand a little bit of this paper, we gotta see the dielectric constants of these solvents. So you see all these solvents go from very low dielectric constants to water that has a really large dielectric constant. I don't know if you can see it very well here, but this is a graph of the solvents. So from here we go from a gas as a solvent, where you see, maybe you can appreciate that the blue is a higher bar in all the steps, even here, and then it goes to a lower state. But that doesn't matter because from here, which is the cleavage of the H2 to catalyze it and reactivate the catalytic cycle again, the gas takes so much energy that it does not matter anymore. That is the lowest afterwards. Then we have then we have other of the solvents. The red bar is the water, and as you can see, the water is pretty consistent being in the bottom, meaning that it uses the less amount of energy to do the same process over here. Even though it takes a fair amount of energy to get the water to do the reactivization of the pyridine ring, it takes a lot less than a gas or any other of the solvents, meaning that the dielectric effect of the water by being very large helps in this reaction. We have to, as any catalytic cycle, we have to regenerate our catalyst. In this case, we can do it in two forms, and they didn't really know why we had two pathways, but in this case we can do it by attacking the pyridine ring first, where this OH minus group is added to the solution. It takes this hydrogen from this part here, which makes no sense because it will take a lot more energy to then break this bond here, to put it back, and then extract this part here. So only part we care about, to have that open side again. Well, you can see that if you do without the piloting ring, then it just goes straight to the side we want it to be reopened again. Okay, this is the fed of how many molecules of water you want to have in your reaction. It's gonna be appreciated in the screen because it looks a little bit blurry. But if you have a copy of this, you can see that 1 molecule of water to reactivate the pirolytic ring. When you add it to the reaction, it takes no energy because you're just adding it. But when it reacts to it, 19.21 kilojoules of energy is needed to reactivate that side. When you add 2 of them, you need 15 kilojoules. But when you add 3 of them, you just need 13. So the threshold here is just 3 molecules of water to do this reaction, which will help to reduce the activation energy of this process. And when you go over, this goes to 30 kilojoules, which will be like a little too much energy for this reaction. And they're trying to make every reaction in this process as low and like as easy as possible because they want it to be like a standardized process, I guess. Okay. Conclusion. Solvents play a major role in this paper or in this like cycle. The heterolytic cleavage of hydrogen, which have 2 pathways, is like the steps that takes the most energy in this process. Here is like a summary of how the reaction happens. So you can see that the CO2 is inserted in the iodine H bond and remove the formate from it. And the second B, you can see how the cleavage mechanism without the pirolytic ring, because they determined throughout the paper that having the pirolytic ring, like having the OH minus attack the pirolytic ring and then go back and like reattach the hydrogen and take the other piece of it didn't make any sense whatsoever. So the last one you see is the one with the pirolytic ring, which they clearly state in red. It says no easy pathway because it's like really tough and really energy demanding.
All
that in 9 minutes.
Go back to your last slide there.
Back?
Yeah.
All right.
So in that second pathway,
This one?
no, B.
That one?
What's getting kicked off on that second arrow? You have A2 hydrogen compound, and then it looks like you have water and hydroxide coming in, and then you get back your trihydride species. What's getting kicked out there?
You mean over here?
I don't know.
It's like a M. Let's go back to your other reaction.
Yeah, it's whatever's coming off that green
And it's like a
arrow.
MH2O
It looks
plus
like
a
a B.
borate ion.
Yeah, it looks like a...
Oh, is B our generic base in this
Yeah.
case?
It's not a like... They didn't care, it just... You need a base to do that reaction. You gotta be under basic conditions, so they have to make a basic.
It looks like B and OH.
No, I think it's so B for like this. So you know how you do HA? It's the same with B.
Oh, right there at the bottom it says B equals OH minus or HC O3 plus.
But
Was that minus or was that plus?
It's probably,
It's a minus.
yeah, it's like
It's just a-
bicarbonate or something.
It's just a basic solution that they're using. And they use OH so they can create water out of it. Monopoly water.
So are they doing this to like gain energy, or are they using this just to decompose?
They're doing this to to use CO2 as a catalyst in this IR3 paradigm
To create water?
No, to create formic acid.
Yeah, they're trying to, in both papers, it's actually fun that they are both on the same day. They're trying to make CO2, which is basically carbon tied up in a worthless form, right? It's already as oxidized as it can get, so it's at its highest energy, we can't do anything with it. So they're trying to, each paper is just trying to reduce it to basically put more functional energy back in. In the case of Alex's, to make methane for the possible use of burning. In this case, it seems more for the purpose of manufacture of, say, industrial chemicals like formic acid, etc. So is your active catalyst is what, that top left one, the trihydride? Is that neutral? It's iridium, right?
Yeah, they didn't specify that. They were just like, this is what you have is just iodine-3 or uranium, like whatever it is.
Right. So is that an 18 electron compound? Is that what we're looking up there?
Mm-hmm.
So we got 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, we got 18.
And I had to look up what a non-innocent ligand means. And it just means that like the oxidation state
It's
is
been around with you.
really clear.
Yeah, it means that it's that it would participate in the catalytic cycle is normally what that means. I guess I go back to the first one of those. So what in the jazz are we looking at?
So this is I thought it was going to be like a lot bigger and less blurry.
Yeah.
This is just the catalytic cycle. I don't know if you remember the paper when we added. So here number 1 is your IR, right, IR3, and then you add your CO2 as a catalyst, which you can see it like over here, which then attaches here. You see it?
Well, it looks like they're one of the hydrides from iridium is popping on here because it looks like it has a green ball on it now, and it went to a trigonal planar structure.
Mm-hmm. And then when it comes down here, it breaks.
It's twisting around.
Yeah, it breaks that bond over there, and then it gets out.
So it kicks that out as HCOO minus.
Mm-hmm.
Okay, and then we have hydroxide coming in here. Is that what this shit is?
Yeah, this OH minus goes in the solution, and that's what reactivates your catalyst. That's where it attaches to it, and then it goes out the water molecule.
I give it a couple minutes.
Okay.
And then you use the H2 as a cleavage to get your formic acid out of the equation, out of the catalyst. And then here you can see it's reactivated again and comes back to step 1.
Huh. And step 1 is, and this is the trihydride. Is that what 1 is supposed to be?
Yeah.
So so at this step, this would just be monohydride, and then it gets both of its other hydrides from A to 2 coordination, and then it cleaves it to give the 3, I guess. What is this massive thing then?
So that massive thing is when, as you can see here, the toluene.
So this is based off of which
Yeah,
solvent molecules being
yes,
used?
that's what I was talking about, like the solvent molecules. And
which one is this one?
the blue one is a gas that they tried to use. And they were like, well, we need a correct load of like energy to get that gas to do this reaction, which that would be the fourth step. No, the fifth step. So this part here. So they're trying to get that gas to do this step of OH minus. Let me see if it works.
Oh, it's that. I guess we're running out of time. I have more questions. But... Dang it.